This is Professor Corey, and this is our third lecture on acid-base chemistry. In our previous lecture, we introduced hydrolysis reactions and looked at equilibrium constants and the relationships between conjugate pairs. In this lecture, we will calculate pH for strong acids and bases, as well as equilibrium constant expressions for weak acids and bases. Remember, strong acids completely dissociate into their ions. We can write this reaction as shown. Notice that it's not an equilibrium. This is because strong acids completely ionize, forming just products. Well, so close to complete that we treat them as though they're completely ionized. This is why the equilibrium constant is so large. pH is the negative log of the hydronium ion concentration. Since this reaction goes completely to products, the concentration of the acid is the same as the hydronium ion concentration. So we can take the negative log of 0.01 to get the pH, which is 2.0. A strong base will completely break apart into its ions. This is not treated as an equilibrium, so our concentration of reactant will be the same as the ions as long as they're in a 1-to-1 ratio. A group 2 hydroxide, like calcium hydroxide, will have 2 hydroxide ions for every 1 calcium hydroxide. For this example, I would calculate the pOH first by taking the negative log of 0.01 to get pOH of 2. 14 minus 2 will give us our pH of 12. And it's basic, as we expected. With a weak acid, we will have an equilibrium because weak acids do not completely dissociate into ions. In this example, I would have to use an ice table and I'd need a Ka value for the weak acid. You may have to look up the Ka value from the chart that we showed in the previous lecture, and sometimes it's given in the problem. We don't have enough information to solve this problem. A common problem is to measure the pH of a known concentration and then be asked to calculate the equilibrium constant K. So the remainder of this lecture will focus on problems of this type. If we have the pH of a weak acid solution, we can use this pH to determine the hydronium ion concentration. This is an equilibrium value, so it's very useful for our ice table. And measuring pH is a relatively easy procedure. In this problem, we have a concentration, which is the initial concentration of the HNO2. We also have the pH, which can be used to find the hydronium ion concentration at equilibrium. The hydrolysis reaction has been written for you, but oftentimes it is not. You may just have the word problem and you'd have to write this hydrolysis reaction. Using the pH, we can determine the hydronium ion concentration at equilibrium. Make sure you can do this calculation on your calculator. The molarity given is the initial concentration for HNO2. Initially, the products are 0 unless otherwise specified. We represent the change in terms of x. In this example, since our products are at 0, we know they will increase. So this change will be plus x. The HNO2 will decrease as the reaction goes to equilibrium. We have the equilibrium concentration of the hydronium ion calculated from the pH. Now we have a method to solve for x. Using the hydronium ion column, we can write 0 plus x equals 0.0060 molar. So x equals 0.0060 molar. Knowing x allows us to calculate all of our equilibrium concentrations, and with these we can calculate our K value. Product concentrations divided by reactant concentrations, and we can write the 0.0060 squared because this is the same as 0.0060 times 0.0060. Go ahead and give this problem a try. I'll give a detailed explanation on the next slide, so pause the video, or if you're not quite ready, go ahead and watch the explanation. If no reaction is given, this is where you want to start. This is a solution of a weak acid, so we want to write the hydrolysis reaction. Next, I will set up an ice table. The concentration given is the initial concentration of the weak acid. The products will start at 0, and water will be ignored since it's not part of the equilibrium expression. The change is represented in terms of x, and we can determine the hydronium ion concentration at equilibrium from the pH. Once we have the hydronium ion concentration, we can solve for x. X equals 5.50 times 10 to the negative 4. Once x is known, we can determine the equilibrium concentrations and write them into the equilibrium expression. The answer is 2.5 times 10 to the negative 6th. 2 decimal places in the pH means we'll have 2 significant figures in our answer. This is a practice problem that I want you to work through. This is a weak acid, and I know that it is an acid because of the pH. It's less than 7, and I know that it's weak because it's not one of the 6 strong acids. The chemical formula is too cumbersome to represent niacin, so represent niacin as HA. Just call it HA, and write your hydrolysis reaction. Next, set up your ice table. You have the initial concentration of the weak acid, the niacin, HA, and you have the pH. Use the pH to determine the equilibrium concentration of the hydronium ion and then solve for X. The percent of the acid that has ionized means how much of the acid went to ion. Use your equilibrium concentration of the hydronium ion divided by the initial concentration of the acid, then multiply by 100. Pause the video, work through the problem. The results are on the following slide. Check your results. Hopefully you were able to solve this problem on your own. In this lecture, we calculated pH of strong acids and bases in solution. We calculated equilibrium constants for weak acids given an initial concentration and a pH value. Same methods are used for weak bases. Just realize that you would have to solve for hydroxide ion concentration, and this can be done from the pH as well by first determining the pOH. In our next lecture, we'll use a method for determining whether a salt solution is acidic, basic, or neutral. Thanks for watching. Stay tuned for more lectures on the Professor's DuBois channel.